Welcome to lesson 40. Yes, this is a typo, so make sure to change this slide to say lesson 40. So in this lesson we will be covering section 5.4 about inference for linear regression. So you are encouraged to read pages 238 to 243 in the textbook. So just as we identified standard errors for point estimates previously, we can discuss standard errors for the estimates of the slope and y-intercept for a regression line. However, in this case, we will identify standard errors using statistical software. When fitting a least squares line, we generally require the following: linearity, so the data should show a linear trend; nearly normal residuals, so generally watch out for influential points; constant variability, so the variability of points around the least squares line remains roughly constant; and independent observations. Be cautious about data collected sequentially in a time series. Such data may have an underlying structure. Below are 4 examples of showing when the methods are insufficient to apply the data in a so in the first panel, a straight line does not fit the data. So here's the straight line, but you can see the data is clearly curved. This means that it fails the linearity condition. In the second panel, there are outliers. 2 points on the left are relatively distant from the rest of the data, and one of these points is very far away from the line. So this would fail the nearly normal residuals condition. However, the outlier does not seem to be extremely influential. It's a little bit influential, but not extremely. The third panel, in the third panel here, the variability of the data around the line increases with larger values of x. So we get kind of this cone-shaped situation here. So this would fail the constant variability condition. And then in the last panel, a time series data set is shown, where successive observations are highly correlated. So you can see what's happening here. It has curves that go up and down and up and down. So this fails independent observations condition. This is a time sequence. And this often happens with stock market graphs. So I could visualize a stock market graph in this situation, because the values of stocks, they go up and down and up and down on a daily basis. So elections for members of the U.S. House of Representatives occur every 2 years, coinciding every 4 years with the U.S. presidential election. The set of House elections occurring during the middle of a presidential term are called midterm elections. In America's two-party system, one political theory suggests the higher the unemployment rate, the worse the president's party will do in the midterm elections. To assess the validity of this claim, we can compile historical data and look for a connection. We consider every midterm election from 1898 to 2010, with the exception of those elections during the Great Depression. So the blue dots represent Democrat and the red triangles represent Republican, and then you've got a couple of years that are attached to some of these data points. So the figure below shows these data and the least squares regression line. So percent change in House seats for President Party equals negative 6.71 minus 1 times the unemployment rate. So the y-intercept here is negative 6.71. That would be an extrapolation because our data set doesn't go that far back. but we did have to, excuse me, we did have to put that in there just for the prediction equation. So here's example 1. Interpret the slope and intercept in the context. Don't just give the value, explain what the slope and intercept mean in the context of this problem. So let's go ahead and do that. So let's first start with the intercept. So when the unemployment rate is 0, the president's party is expected to lose 6.71% of their members in the House. Okay, again, this is an extrapolation, so we don't want to put a whole lot of faith in that number. All right, now let's interpret the slope. So for every 1% increase in unemployment rate, the percent change in House is negative 1% for the president's party. Examining the data, there are no clear deviations from linearity, the constant variance condition, or in the normality of residuals, though we don't examine a normal probability plot here. So everything is pretty balanced above and below this line. This is a time sequence, so we might have an issue there, but so far so good. While the data are collected sequentially, a separate analysis was used to check for any apparent correlation between successive observations. So because that was done and no such correlation was found, then we're okay with the fact that this is a sequence. So conditions for linear regression seem to have been met.